Okay, do you still see my screen share? Oh, no, not yet. Let's go back to. Okay, so this is just a comparison of the derivative and differential rule here. This is the thing that you see from the well in physics measurement, how to compute errors. All right, we're not talking about this one first. Let's just do approximations here. This is approximate by this one here. So this is our approximations. Okay. Let's do some more problems. Okay. All right, let's do this one here. Problem 20. Okay, so approximate the 26.91 square root of square root 3. Okay. So that's okay. Here. All right, so because this is approximations, there is no whether it is correct or incorrect, but it is good or even better. Okay, better approximations. All right, so this one here. So first guess, what is the uh, the the number that you expect if you just compute it just by mentally by
3.
hand?
Three?
Three,
Three
around three,
or
right?
less?
Less than, slightly less than three. So we are trying to make sense of what that slightly less than three means. Okay. So this less than three. Okay. So what does it mean? Okay. So let's do this one. All right. So let's set a function first. What kind of function do you set? So you set up here. What's the function?
Is it the cubic root of
Yeah,
x?
exactly. Okay. So then when you say that three, what number you're thinking about actually? When you say that it is around three. If this exactly three, what number you're thinking about?
27.
That's 27. So that's the easy one. Okay. So we need to compute okay. So let's see. From here we get the derivative is say this is 1/3, right? So this 1/3 is negative 2/3. Okay. And see. So our dy, no. What you compute is actually, what we need to compute is delta, but this delta is approximated by d. And because we know this is computable using this, say this is times delta. Oh, we got something here. This 29.91 is the x, okay? And that is the a plus delta x, right? So here, delta x is negative uh, 0.09. Okay, so this is our delta x. Okay, so just plug in the number now. So 3 times, let's see, cube root of 27, that's 3, square root 9. Okay, and here we get, yes. So what you have here is 27. There we go. Okay, so our, this is the, okay, the original problems now is that 3. How we get that 3? That's the, that's cube root of 27. But this is 3 negative. Okay. So let's see. What is this number here? 9. It's calculated. Point, 09 7. Okay. It's negative. Mm, oh, this is repeating. Okay, so what you get here is that times six, like that. Okay, and if you make a comparison, actually, you get cube root. Do you have calculator? Can I compute? Do have calculator that has that easily?
The answer for calculator is 2.9966.
2.99.
66.
Right, so at least it is correct until three digit behind zero. Okay. That's good enough. All right, any questions? One more example. Okay. Let's see. This one. Oops, that one. Sorry, what? Not this one. Let's see. Let's see. All right. See this number 25 here. Okay. So this equator is the circle's radius is approximately 4,000 miles. Okay. So how much longer than the equator would a concentric coplanar circle? Each point we're 2 feet above the equator. So let's see. Let me just retelling you the story. Oh. Okay, say you want to wrap a ribbon around along the equator of the globe. Okay, so this is the equator. So you want to wrap that around. Okay. So wrap that around, just fit into with the radius tightly. Okay. And you see the ribbon was paid already. Okay. Ribbon required is paid already. All right, so the thing is that I'm saying that, all right, so if the ribbon is now should be, say, 1 meter hanging, I would say that the willing pay for extra ribbon. So that the is not wrapped tightly, but hanging 1 meter above the equator, above the ground. Okay. The thing is, how much should I pay? Okay, ribbon is cheap, but the thing is, that's along the equator. Okay, so uh, do you think I would pay really a high price, or uh, what do you think? Is that going to be a large sum of money or what? Guess first. Do you see the problem? What you need to compute?
Was it number 25, sir, in the book?
Let's see. 25. I just retelling you the story. Okay, with basically the same computations. Okay, so wrap the equator around tightly with a ribbon. Okay, so the ribbon is paid off. Now that let's make the wrapping is not tight, but about 1 meter hanging above the ground. Okay, so I'll pay for the extra. Okay, so the question is, how much should I pay for that approximately? Do you think it's going to be a large sum or not? Right, so let's do this one. Of course, you can do a computation exactly. Okay, that is uh, to compute. Right, so this is 4,000 radius is 4,000 miles. So that is all right. So 1 meter compared to this 4,000 miles is really small, right? So we would like to make this into x plus delta x. This is the error, okay? And we would like to find y delta y. But delta y is then going to be approximated by dy. So we need to find the function first. Okay. So what we have here plus 1 meter. Of course, the unit's not equal yet, so we need to do that later. So this will be the x, say a. This is our delta. Because this is small, you can think this is error. So the thing is, we need to approximate delta y. Of course, if the computation is easy, you can compute directly delta y. But we need to just do the sum approximations. Compute dy. Okay, so what is the y? So what should be the functions? The function should express what? What should be the function about?
2 pi r.
What is 2 pi r? I'd like to
The
tell you
slope.
what's the What is 2 pi r?
The circumference?
Circumference, the length, right? The length
Yeah.
of the ribbon. Right? So that's 2 pi r. Okay. So what we have here is that, okay, so 4,000 miles, say this is 1.6, 1.6, 6.4 kilometer, 10 to 3 meter, plus 1 meter. Okay, so there's 2 pi r. All right, so when you compute dy, that's easy because there's only 2 pi. Yeah, that's it. 2 pi r. Okay. See, this disappear. So when you compute this one here, this is our dr. Sorry, this should be, just make it r. Okay, so what I'm saying here is that I'm willing to pay for that extra length, right? I'm willing to pay for an extra ribbon. So the extra ribbon is that all right. So what we got here is that, well, this not depend on the does not depend on the does not depend on r. Okay, so our dr is 2 pi 1 meter. So what you get is 2 pi meter. So only six something meters, less than 7 meters. Okay, so it's turns out that you don't have to pay a lot for that extra length. It's just only for about slightly more than 6 meters. Okay, so about 6.8 meters of extra length. Okay, questions? Questions?
No, sir.
All right, let's review something here. All right, if not, then let's start with the new chapter. So it's chapter on the application of the derivatives. Okay, let's do this one here. Let's review what we have in the next chapter. Okay, So next, what we will cover quite quickly is that the 31, 32, 33, 3, this plus this one. Quickly. Okay. And practical problem, that word problems, we'll do that later. Okay. So let's all right, let's start this with the minima and maxima. The question is about how to find a maxima and minima of a function. So try to locate maximum and minimum. Okay, so given a function f, a domain S, the question is, does it have maximum, minimum? And where are the maxima and the minimum lie? And how can we find them? Okay. So what is maximum? Maximum value is the highest value. So if you compare to other value, it is bigger, always bigger. Minimum is always smaller. Okay, what we call extreme is either maximum or minimum. Okay, and the function to minimize or to maximize is the what we call objective function. So F is objective functions. That's the naming of the object. Okay, so for example here, you see these functions given a graph. Okay, so we try to find a locate maximum. All right, so the maximum looks like here. That's the highest. And the minimum will be here. That's the lowest. Okay, so it does have the function does have the minimum maximum distance. Okay. So the thing here, we need to find this one here. So this one extends to the right and extend to the left. Of course, in this case, here, there will be no max nor min because it always goes lower and lower. It goes higher and higher. There's no max nor min. Okay. However, if we say restrict it on y3, one between 1 and 3, you see to the left, that's the highest point. That's the maximum. If the lowest would be on the right. That's the minimum. Okay. So you see here, maximum minimum really depends on whether the set here. Some set allows you to have max min. Some set just don't allow. Okay, you see that this max min here. It's continuous, so that's the conditions. Must be continuous. Closed interval. Then, um, then for sure, F has both maximum and minimum in that case. Okay, so why this one has no max min on the whole thing? Well, because the function's continuous, okay, but here's the 0 to infinity. It should be this one's like this one here. from something to something. So it must be closed interval. So as long as you work in closed interval, then you're looking at next one. The thing is, how do we locate extreme values here? Okay, so here peak, and here you get, but in this case, the highest value is not on the peak, but here. Okay. In this case, well, you're right. Here we have the max be on the peak. This on the peak. So, okay. It actually occurs. All right. So observations on the peak, you see that if you draw the tangent line, looks like this one. Also here. Here, no, you cannot draw the tangent line here. No tangent line. Okay, so our special concern is when the function is zero, so this slope zero, because a horizontal line is slope zero, or no slope, no tangent line. That means the function is not has no derivatives there. Okay, so what we need is derivative equals zero, what we call a stationary point, and derivative doesn't exist, what we call a singular point. Right? So that is our what we call critical point. Right? So the idea is later on is find critical point. That would be the candidate for max win. All right, so that's the strategy that we will use later. Okay, I'll stop here and continue with this with the computational part tomorrow. Okay. Later you have the exercise with Kakemal about the problems. All right. Any questions?
Sir, one question.
Mhm.
About the quiz later. We're gonna do the first quiz, the first session in 3 o'clock, right? The second
Oh,
session is
the second. Oh,
oh,
sorry.
like
First,
the
first at when you mean attempt or the
my
session?
first yeah, our first attempt is gonna be done at
Yeah,
3 o'clock, right?
three. Yeah, three.
So do we stay in the meeting when we do the test, or can
No,
we?
no. Just
Oh,
just log out of the meeting and then just log into the LMS.
oh, okay, okay. Thank you, sir.
Any more questions?
Sir, I wanna ask,
Uh-huh.
why figure 6 doesn't have a tangent line, sir?
All right. Yeah. Remember, no, tangent is where the function is differentiable, right? The thing, so the question is, what happened to the graph if it's not differentiable? Remember the three cases when it's not differentiable? No, not continuous, first one. And let's see what else? Or you have a vertical tangent. So not differentiable. um, I'm just use a scratch this one here, not differentiable. First case is you can say vertical tangent. So it looks like this one here. Yeah, that's vertical tangent. It's not differentiable. So this is singular. Or some the hair is sharp like this, sharp point. Okay. That means the from left and from right here, it has different tangent. Okay. Sharp bend. Or something that's not continuous. Okay, like this one. It's not continuous. Okay.
Okay, thank you, sir.
But even though this is not, there's no tangent line, this is still maximum. This is still minimum. Okay. So regardless of tangent, we still have minimum maximum. All right. So then we'll stop here. I'll then see you later then. Okay. All right. Thank you. I'll stop the share. And